So up until this point, we looked at various transformations of parent functions. So the very first section, 3.1, where we looked at the functions at x cubed, or the cubic function, the square root function, the absolute function, and the reciprocal, or 1 over x function. Looking at those parent functions, then we looked at later on the transformations, both horizontal and vertical compressions, stretches, or reflections, and also horizontal and vertical translations, and there's shifts of the graphs, how affected all four of those parent functions. We also looked at 3.2, exponential functions, just what a base exponential function looks like. So it only makes sense that we're also going to look at transformations of exponential functions as well. We're going to see that this works a little bit different in terms of the other ones, in terms of really identifying what the parent function is. But really, our mapping notation, which we talked about 3.5, in other words, getting our A, K, C, and D attributes from the function. Once we have that mapping notation and the points on our parent function, everything still works the same after that. So really, the big difference here is going to be just really identifying what the parent function is and the key points on that parent function. So as a warm-up, we're going to just go back and refresh our memories of what an exponential function might look like. So we're going to look at one instance where y is equal to b to the power of x. Again, this is the definition of an exponential function is here x, our variable, is in the exponent and not in the base. So when y is b to the power of x, one instance is when b is greater than 0, and another instance when y is equal to b to the power of x again, but the base here in this case is between 0 and 1. So what might we come up with our value for b greater than 1? Well, we could look at y is equal to 2 to the power of x, right? So b here is greater than 1. In this case, it's 2. So if we're unsure on how to graph or forget what the graph looks like, we could always fall back to our table of values. So here we get x and 2 to the power of x, and sort of the key x values for our exponent. And this is going to apply to, doesn't matter what our b value is these are the key x values in order to get a graph of the exponential function. Is x being 0 because we have the exponent 0, 1, 2. We may go in the other ways because we could have negative exponents as well, is -1, -2. So in this case, let's start with 0. 2 to the power of 0 is actually 1. Anything to the power of 0 is 1. 2 to the power of 1 is 2. And 2 squared is going to be 4. Going in the negatives, we got 2 to the power of -1. So remember, a negative exponent means that we reciprocate our base. So our base here is 2 over 1. So this is going to be 1/2. And we reciprocate our base, our exponent becomes positive. So 2 to the power of -1 is just 1/2. 2 to the power of -2 is, again, we're going to reciprocate our base. In this case, it's going to be 1/2 now. The exponent becomes positive, so that's going to be to the power of 2. So 1/2 squared is 1/4. So now we go off and plot that in our graph. So we get x and y. Let's do our scale of 2, 4, 6, 2, 4, 6. And let's plot this. So we got 0, 1. That's 1 point. Then 1, 2 will be right there. And then 2, 4. And then going the other direction with the negatives, we got -1 is 1/2. And -2 is going to be 1/4. So one of the things that we want to remember, because it's going to be important for graphing it, is the exponential functions. All exponential functions do have a horizontal asymptote. And the reason is because we can see as we're going through each of these, when we reciprocate, the denominator is going to get bigger and bigger and bigger as x gets smaller, but we can never have 0 because we have 1 in the denominator. So it's sort of like the reciprocal function. And in fact, the exponential and the reciprocal are very closely related in that sense, because they both have the horizontal asymptote for that one reason, that when we reciprocate the base here, we're going to have 1 on top, or at least 1, so we can never get 0. So let's draw in the horizontal asymptote. Happens to be right on our x-axis. or in this case, the equation of y is equal to 0. So let's join the dots, knowing that this is going to be a smooth curve. So we're going to be close and close to the asymptote, but not touch it, and then the exponential will go up very quickly. Okay, so that's what y is equal to 2 to the power of x looks like. So we call this an increasing function because as x gets bigger, or as the graph moves to the right, y gets bigger as well. Let's look at, let's do this in red. So when b is less than 1 but greater than 0, so maybe an example of that would be maybe 1/3 to the power of x. So I think in the notes that we did in 3.2, I used 2 to the power of x and also 1/2 to the power of x. We saw that there's a direct relationship between those two. Here I'm going to just choose a different fraction of y is equal to third. Sorry, y is equal to 1/3 to the power of x. So in order to come up with this graph, we could do the same thing, come up with a table of values. So here y is equal to 3 to the power of x. So we still have the same x values of 0, 1, 2, and -1, -2, because we can have negative exponents as well. So 1/3 to the power of 0, that's going to be 1. 1/3 to the power of 1 is going to be 1/3, and 1/3 squared is going to be 1/9. So here, the tricky part here is the negatives again, so we need to reciprocate our base. So this time our base is 1/3. So when we reciprocate 1/3, we're going to get 1. So that's really going to be the same thing as 3 to the power of 1, which is just 3. And likewise, 1/3 to the power of -2, we're going to reciprocate our base. We're going to get 3, and our exponent becomes positive. So this is going to be 3 squared. So that's going to be 9. So let's go off and graph that. So we still have the point 0, 1. And then you got 1 and 1/3. So 1 and 1/3 might be like right there. And then 2 and 1/9 is going to be really, really close. So notice that here we have the same asymptote because it's going to get closer and closer to 0, but not touch it. So going in the negative directions, we got -1 and 3. So -1 and 3 would be right there. And then -2 and 9 will put us all the way up there. So you can see here, it becomes really sharp a lot faster than y is equal to 2x. And we can kind of see why, because we reciprocate 1/3, it's going to be a 3. Right? So again, this could be a direct relationship in some ways to y is equal to 3x, and with y 3x is going to be very sharp as well. So let's graph this. Let's connect the dots. So again, we have the exponential function that it's going to be a smooth curve, but it's going to get closer and closer to the asymptote and not touch it. I think I touched it by accident, but we get the general idea. Okay, so what we see is that with the base is between 0 and 1, but this is what we call a decreasing function. And as x gets bigger, our y values get smaller. So it's going to get closer and closer to 0 on the right. Okay, so there's a review of what I may call the base or the parent. We're going to discover these are the parent exponential functions. And so all exponential functions will look this way. It's either going to be the blue, where it's going to go up as we go to the right, or it's going to look like the red, where it's going to come down and as we go to the right. So our success criteria for today, for this section, is we're just going to describe and graph transformations. And now we're focusing directly on exponential functions. So in order to explore transformations of exponential functions, we're going to look at a couple examples. So in the first one, we're going to consider that f of x is equal to the power of x. So really, that's our base. So one thing I just want to emphasize when we look at exponential functions, every exponential function with a different base is its own parent function. So that's one of the big differences when we look at exponential functions compared to the other 4 that we looked at, the cubic, the reciprocal, the absolute, and the root, is that those only have one parent function, and therefore it has those same set of values when we transform them, when we use mapping code to transform them. However, with the exponential function, every single value of b is going to be a different parent function. So if we look at a warm-up, what we're saying here is that y is equal to power of x. That is a parent function. We would transform that function 2 to the power of x. Or there will be another parent function of 1/3 to the power of x, and then we could transform that. So the transformations might be the same, but our initial parent points are going to be different because the base is going to be different. So in our example here, we say that f of x is 2 to the power of x, so that's my parent function there. Our transformation here is going to be -3 f of x plus 1. So just like before with the when we did combinations, we just go off and pick off the a, k, c, and d attributes. So here a is -3 because it's -3 multiplied to outside of the function. K here is going to be 1 because we're not multiplying anything to x, or just going to be really just 1. Our d value is 0 because we're not adding or subtracting anything to x. And here my c value is a positive 1 because we're going to add 1 outside our function. So if we go back to our mapping notation, I'm going to write the mapping notation maybe over here. So again, our general formula, and keep writing this so that it sticks in our head, is going to be x over k plus d, then a times y plus c. So given x comma y on the function that we're transforming, in this case 2 to the power of x, in order to get the new points on our transform function, in this case g of x, we apply x over k plus d to every single original value of x on our parent function, and then a times y plus c to every single y value that we got on our parent function. So here, just after that, it's just plug it in and replace our value. So in this case, k is just 1, so it's just going to be x over 1 or x, and d is 0. So we're not adding, subtracting anything to x. So really, we're not doing anything to x, and we can see that in our function notation. Nothing is done inside the brackets to x, it's just x. However, we do have vertical transformation. So here a is going to be -3, and then times y, and our c value is plus 1. So that's how we get our new y values is -3y plus 1. So so let me write that down over here. I'm supposed to also write the expression. So let me just move this up here. So how do we write this as an expression of for g of x? Well, this is going to be -3. In this case, what's our actual function? Well, 2 to the power of x, but let's put that in brackets to separate the -3 and 2, or else it's going to look like -32 to the power of x. So we need that set of brackets there. So whether you put it around the 2 to the power of x or put around the -3, it doesn't really matter. And then we have plus 1 on the outside. So we just did our mapping notation. So let me just copy that down over there. So x comma -3y plus 1. And it's convenient to put it right beside our table because that's where we're going to be doing our calculations. So here, in terms of getting our graph, I created a single table for us, so everything's kind of in one place. So in this part, we need x and f of x, which is really looking at my parent function, or the function I'm transforming. In this case, that's 2 to the power of x. So we're going to have the same values as we had in our warm-up, because that's what we use for b is 2. So again, we're going to use x as 0, 1, 2, and -1, -2 for the values for x. There are exponents. And so f of x here again, here is going to be 2 to the power of 0, which is 1. 2 to the power of 1 is 1. And 2 squared, or 2 to the power of 2, is 4. And then going in the other direction, we saw that 2 to the -1 was a half, and 2 to the -2 was a quarter. So those are my original points that I need to transform. And how am I transforming them? Well, I'm using the mapping notation that we have provided here. So here, let's go off and, so our x's don't change, so I'm really just copying it down. But we need to go off and calculate g of x. So one thing, again, I get this asked as well, could I take -2 and plug that into my expression over here? And would I get the same answer? Yes. But recognizing that actually this is a little bit more work as opposed to just using this part over here, -3y plus 1. So I'll do that part. So -3 times a quarter, that's going to be -3 quarters plus 1. So that's going to be 1 quarter. And then negative 3y times a half, that's going to be negative 3 halves, plus 1, so that's going to be negative 1 half. Then we get negative 3 times 1, which is going to be negative 3 plus 1, that's going to be a negative 2. And then negative 3 times negative 3 times 2 is a negative 6 plus 1, so that's going to be a negative 5. And last, negative 3 times 4 is a negative 12 plus 1, and that's going to be a negative 11. So here we get the new points, negative 2, and I'll maybe write this out explicitly, negative 2 comma 1/4. We have negative 1 and negative a half. We have 0 and negative 2. We have 1 and negative 5. And we have 2 comma negative 11. So let's go off and graph that. So there's my x, there's my y. Let's go up by 2 ones again on my grid. So 2, 4, 6 for each 2 lines there. 2, 4, 6. And then let's graph this. So one thing actually before I graph this is I'm going to draw that horizontal asymptote. So remember, for all exponential functions, we have a horizontal asymptote. So normally this is at y is equal to 0, as we saw over here. But this graph, in this case, or transformation, so it's like the reciprocal. This one is shifted up 1 because our c value is 1. So our horizontal asymptote is going to do the same thing. So here I'm going to draw the horizontal asymptote then at y is equal to 1. So y is equal to 1. And so we got to make sure that we never touch that line, and really recognizing that the entire graph is either going to be above this line or below this line. And here we see that this is actually vertically reflected because a is negative 3. This is going to be below the line then. So let's go off and plot this. So I get negative 2 1/4. So negative 2 1/4 might be like right there. Then we get negative 1 and negative a half. So negative 1 and negative a half would be right there. 0 and negative 2 would be right there. And then 1 negative 5. So now it's again coming down really quick. So 1 negative 5 over there. And then negative 2, 11 is actually off my grid, but it's approximately over there. So now we know we're going to connect these points in a way that looks like the exponential function. So we know that it's going to be closer and closer to the horizontal asymptote, and then it's going to start breaking off away from it in a rather fast way. So there it is. There's g of x. Okay, so that's what we're dealing with. Just the vertical translation, so just having an a and c values. Our next example we're going to look at is, well, f of x is 3x, but here's the transformation. So g of x is f of 3x plus 6. So knowing that now we have something inside the function, we got to look at the k value, and if there's something added subtracted to x as well, we need to factor out the x. So factor out the k value. So I'm going to rewrite this. This is really f of, going to factor out a 3, and here we get x plus 2. Because if we don't do that, then we're going to get the wrong horizontal shift. So let's go look at my a, k, d, and c attributes. So in this case, a is 1. Nothing's being multiplied by my function. And let's jump straight to the c. Recognize that nothing is being added as well. So here we're just looking at a horizontal and what that looks like. And I just want to focus on that because this part's a little bit tricky. So my k value here is 3, and my d value, again, we're looking at inside that, and what value of x makes that 0. What value of x makes that 0? We're going to ask ourselves that a lot. What value of x makes that 0? Well, in this case, that's going to be negative 2, so that's where we get the right shift value. So here my parent function is 3 to the, let me rewrite this expression. I keep forgetting some of this. So this is the tricky part. So here g of x is, well, I still got 3, so that's my base, but x is my exponent, but we're doing something to x. We're doing something to x. In this case, we're multiplying x by 3 and then adding 6, but this is all happening in the exponent. So this is where it kind of looks weird, because now we can get 3 to the power of 3x plus 2. Which, oops, not 3, we need the brackets there. Which, or we could say same thing as we had originally, 3 to the power of 3x plus 6. Okay, so either one will work. Obviously, this one is more preferable because we could actually see the k and the d values better. The mapping notation, well, again, the mapping notation is x comma y goes to x over k plus d, a times y plus c. So in this case, we're going to see that k is going to be 3, so x over 3, and d is a negative 2, so we just subtract 2, and we haven't done anything to y, so y is just going to be the same. So let me just rewrite that down here. So x over 3 minus 2, and then we're just left with y. So we'll go off to graph this. Again, we just need to look at our parent function, the points in our parent function. So here we're going to get 0, 1, 2, negative 1, negative 2 again. So 3 to the power of 0 is 1, 3 to the power of 1 is 3, 3 to the power of 2 is 9. And then going the other direction, 3 to the power of negative 1 is going to be a negative a third. And then 3 to the power of negative 2, oops, not negative a third, it's a positive. And then negative 2 to the power of, 3 to the power of negative 2, that's going to be 1 over 9. So there's the points on my original or f of x, my parent function. Now we have to transform that with our mapping notation. So here y is just the same, hasn't changed. So we're just going to copy over the y values. But now we have to transform or get new values for x. So here we're going to replace x with negative 2. So it's going to be negative 2 thirds minus 2. So that's going to be negative 2 and 2 thirds. Then we have negative 1 minus 2. Oh, we need to, it's going to be negative 1 over 3. Sorry, my bad. Negative 1 over 3, because it's over k, minus 2. So it's going to be negative 2 and 1 third. That looks like an exponent there. Let me rewrite that. So negative 2 and 1 third. X over, 0 over 3 minus 2. So it's going to be 0 minus 2. That's going to be negative 2. And then 1 third minus 2. So this fraction is a little bit more tricky now. So 1 third minus 2, that's going to be negative 1 and 2 thirds. And then finally, we get 2 thirds minus 2. So that's going to be a negative 1 and 1 third. All right, so let's go off and graph this. So there's my x, there's my y. Let's go with the, well, just to see what's happening or everything, let's just keep it the same scale. So 2, 4, 6. Although we're going to see this could be a better choice because really we're seeing all our x values are all between negative 1 and negative 3, right? It's all within really tight in there. And we're going to see that when we actually plot it. So here we're going to get negative 2 thirds and 1 ninth. Oh, so let's look at the horizontal asymptote. Well, because this graph has not moved up or down any, well, that means the horizontal is still on my x-axis. In other words, still equals y is equal to 0. So here I get negative 2 thirds and 1 ninth. So negative 2 is there, negative 4 is there. So negative 2 and 2 thirds and 1 ninth. So it's going to be really close to my asymptote, and maybe that's right there. Negative 2 and 1 third and 1 third. So maybe that's right there. So really tight in there. Negative 2 and 1. It's going to be right there. Negative 1 and 2 thirds and 3. So negative 1 and 2 thirds and 3. That's going to jump all the way up here. And then negative 1 and 1 third and 9. We're going to jump all the way up there. So that's really tight dots there. Do my best, connect it like an exponential function. Bend the curve there and then flatten out really quick. All right. So that one's really tight because all those dots are really kind of close together. And we can see why, because our k value is 3. That means this is horizontally compressed. So yes, we definitely see that as we're plotting it. And the factor again here is by a third. So that's what a horizontal compression in this case, and a shift or translation for exponential function. All right. So let's go off and summarize this. So when we have g of x is a times, so in other words, an exponential function b to the power of x minus d, sorry, b to the power of, k times x minus d plus c. All the vertical and horizontal compressions, stretches, reflections, shifts apply to f of x is equal to b to the power of x. So the key is really trying to find what that parent function is. Okay, we're going to see an example underneath. Yeah, so we're going to see an example of how we might do that, because once we have, the a's in there, it looks kind of tricky. Or worse yet, we might have something like this: y is equal to 5 to the power of x. Let's use 5 now. Let's just do another example. 6 to the power of x. People mistakenly says, well, this is the number, so it must be a. So we make that mistake. But in this case, since it's 6 to the power of x, it's actually the base of my exponent, so it's really b. And we're going to see here that the a value is actually 1 because we're not multiplying anything to that. So let's go through an example where we write the equation. So here's a parent function, f of x equals 5x, that results in each of the transformations applied to this. So I like to read this, what the transformation is, understand what attribute I'm focusing on, and then what that value of that attribute might be, and then write the equation for that. So here, when it's reflected in the y-axis, that means it's horizontally reflected. That implies that k must be negative, and since we're not given a stretch or compression factor, we're just going to assume that k is negative 1. So in this case, g of x is equal to 5 to the power of, so remember k is affecting x directly, and since x is the exponent, it's going to be 5 to the power of negative x. Here, it's compressed vertically by a factor of 1/7. So compressing vertically, that really affects my a. And since it's the a, the factor is the actual a value here. So if I have a factor of 1/7, and it doesn't say that it's vertically reflected or anything like that, so we're just going to leave it as a positive. So g of x here is going to be 1/7. And this is the tricky part. In this case, I'll put 1/7 around the bracket to the power of 5 to the power x. All right, so that's how we can see this a value is sitting outside the power there. Horizontally stretched by a factor of 9. So this one's tricky. Horizontally stretched, we know this is going to be my k attribute by a factor of 9. So that means that k is going to be 1 over this factor. So it's really going to be 1 over 9. So that's my k value. And then it's translated down c units. So translation down, that's really the c value. C attribute, so it's down, that means it's going to be negative 9. So that implies that g of x is going to be, so my k value is going to be 1/9, so that's in my exponent, so I have to write this carefully. So this is 5 to the power of 1 over 9 x, and then we subtract 9 on the outside. Okay, so that was again tricky only because now we're dealing with k, which just means that this is up in the exponent. So that's actually kind of hard to read. Let me try to do that again. So 1 over 9. So hopefully that's comes out a little bit better when I zoom back out. So yeah, a little bit more legible, 1/9 x. So reflected in the x-axis, so this is actually a vertical reflection, and that means it implies that my a value then is going to be negative, and since it's not stretched or compressed, we're going to assume that's negative 1. It's shifted to the left by 10 units. So to the left, that means that d is actually going to be negative 10. So how does that look like? That means that g of x is going to be negative 5. I could put a negative 1, but we don't write the 1. In this case, I don't need a bracket because since I'm not putting the negative 5 on brackets, we know that the x is going to apply directly to the 5. So here it's going to be x minus d. So in this case, since d is negative, this is going to be x plus 10 as the exponent. Compressed horizontally by a factor of 1/3. So again, this is going to affect my k value. So since the compression factor is 1 over k, we reciprocate this factor over here, so that gives us a k value of 3. And then shift it up 2 units, so that implies that c is going to be 2. And to the right 3.5 units, that implies that d is going to be 3.5. So here g of x then is equal to, I don't have an a value, so here I'm just going to have 5. My k is 3. So this part is tricky because now I need a bracket here, x, whatever my horizontal shift here, so that's going to be x minus d, so it's going to be x minus 3.5. So we need that in the brackets before we multiply by 3, and then shift it up 2 units, so we're going to add 2 on the outside. Okay, so that's what that expression looks like, that equation. So when we're dealing with the exponential functions or transformations of it, that's the confusing part, because now our exponent is just not a simple letter or a simple number, but it's actually another expression in there. So here we want to state the parent function in the mapping notation of g of x is equal to this. So let's go off and identify the parent function first. So here it's the exponent. So what's immediately to the left of the exponent? It's actually 5. Okay, so that's where the parent function is. F of x is equal to 5 to the power of x. Happen to be the same as above, but that's fine. So now we have to go off and pick off the a, k, d's, and c's in order to get our mapping notation. But even before I do that, recognizing that in my exponent, we'll have a k value, and we need to factor that out. So here I'm just going to write at top, we got negative 4x minus 6, so we want to factor the negative 4. So that's going to leave me of x plus, so really negative 6 divided by negative 4 is going to be a positive 6 over 4, or 3 over 2. So I'm going to rewrite here as g of x is equal to negative 2 times 5, in this case to the power of negative 4 times x plus 3 over 2. And then we have minus 1 on the outside. So here, let's go off my a attribute. It's going to be negative 2. The k attribute we saw is going to be negative 4. My d attribute, so again, tricky part about d is what makes that 0, what makes that 0, what makes that 0. So what makes x plus 2, x plus 3 halves equal to 0? Well, x must be negative 3 over 2. And then my c value is here is just negative 1. So how can I express the mapping notation? It's going to be x over k, well it's actually x comma y, 2, x over k plus d times a times y plus c. So that maps to, in this case specifically, negative x over 4, because we're dividing by negative 4, plus d, so in this case it's going to be minus 3 over 2. And then to get my a value, my y value is going to be negative 2 times y minus 1. So there's our mapping notation. Final answer right there. Last but not least, we're going to, without graphing, because graphing this would be kind of tough, lots of fractions in there and everything. How can we state the domain range and the asymptotes, if any? Well, it's going to be an asymptote because we're dealing with an exponential function. And we know it's going to be a horizontal asymptote. But let's do the range first, or the domain first, because that's the easiest one. For every single exponential function, doesn't matter how it's transformed, x could be anything. So xer. You can have any value of x in there because you have any number for an exponent. The range and the asymptotes are directly related. So I'm actually going to do the asymptote first because that's easy for me to visualize. So normally asymptote is y is equal to 0. In other words, right on the x-axis. This is going to be directly related to whether this graph or the transformation is shifted up and down any. So in this case, it's actually shifted down 1. So therefore, my asymptote will come down 1 as well. So since our original asymptote equation is y is equal to 0, straight going down 1 just makes it y is equal to negative 1. So we recognize or see that there's a direct relation between my c value and the equation of my asymptote. Really, it's the same thing. Well, because now that we see that the asymptote is there, well, the range is, well, we know in our parent function, it's either going to be above or below something. Everything is either above 0 or below 0. Sorry, in the parent function, everything's going to be above 0, but if we reflect it vertically, then it could be everything below 0. So y has to be greater than or equal to something. But in this case, is it being reflected, vertically reflected? And we see that it is. So instead of being above something, it's actually going to be below something. So it's going to be less than negative. And again, this directly relates to asymptote. It's going to be strictly less than -1. So that's how you kind of come up with the domain range and the asymptotes. For this one without having the graph, and I would argue that you could probably visualize, or hopefully could visualize it for this with any function. So whether it's the root, the reciprocal, the absolute, or the cubic, is that depending on the transformation, if we know what they are and the characteristics of those parent functions, we could get the domain and range and the asymptote if applicable for any functions based on its transformation.